How did everything start from nothing? Particle physics is a branch of science that delves into the world of the very small, exploring the fundamental particles that make up the universe and the forces with which they interact. Unlike the familiar objects of our daily lives, which are governed by classical physics, the subatomic realm operates under the rules of quantum mechanics, revealing a world that is both fascinating and counterintuitive. At the heart of particle physics is the quest to understand what the universe is made of and how it works at the most basic level. Scientists in this field study particles like quarks, electrons, and neutrinos, which are the building blocks of atoms, themselves the building blocks of matter. These particles are incredibly small, so much so that their properties and behaviors challenge our conventional understanding of space and time. One of the most significant achievements in particle physics has been the development of the Standard Model, a theory that describes the fundamental forces, except for gravity, and particles that constitute the universe. According to the Standard Model, there are four fundamental forces: the electromagnetic force, which causes electric and magnetic effects; the weak nuclear force, which plays a role in radioactive decay; the strong nuclear force, which binds quarks together in the nucleus of an atom; and gravity, which is not yet fully explained by this model, but is known to govern the attraction between masses. The Standard Model has been remarkably successful in predicting and explaining the behavior of particles in countless experiments, yet it is not the final word. Scientists are still searching for a more complete theory that can include gravity and account for the mysteries of dark matter and dark energy, which make up most of the universe's mass and energy, but remain elusive to direct detection. Research in particle physics requires incredibly sophisticated technology, such as particle accelerators and detectors. These machines accelerate particles to nearly the speed of light and then collide them, allowing researchers to observe the resulting interactions and particles that are produced. The Large Hadron Collider, LHC, located near Geneva, Switzerland, is one of the most powerful particle accelerators in the world. It was here that the Higgs boson, a particle predicted by the Standard Model that gives other particles mass, was discovered in 2012. This discovery was a monumental step forward, filling a crucial gap in our understanding of particle physics. Despite its complexities, the field of particle physics is driven by a simple and profound question: what is the universe made of? The pursuit of an answer has led to groundbreaking discoveries and technologies, including the World Wide Web, which was initially developed at CERN, the European Organization for Nuclear Research, to facilitate information sharing among scientists. As we delve deeper into the mysteries of the universe, the intriguing intersection between cosmology and particle physics becomes increasingly apparent, weaving a complex tapestry that spans the vastness of space and the minutiae of subatomic particles. Cosmology, the study of the universe's origins, structure, and evolution, finds a surprising partner in particle physics, with its focus on the fundamental constituents of matter and the forces that govern their interactions. This synergy opens up new pathways to understanding not just what the universe is made of, but also how it began and has evolved over billions of years. At the core of this intersection is the Big Bang theory, a cornerstone of cosmology that posits the universe started from an incredibly hot, dense state approximately 13.8 billion years ago and has been expanding ever since. Particle physics enhances our understanding of this primordial moment by examining the behavior of particles at extremely high energies, similar to those that would have existed just fractions of a second after the Big Bang. For instance, the conditions of the early universe are recreated on a miniature scale within the colossal particle accelerators like the Large Hadron Collider, allowing scientists to study reactions that occurred in the universe's infancy. One of the most fascinating aspects of this intersection is the exploration of dark matter and dark energy, mysterious components that together comprise about 95% of the universe's total mass and energy. While dark matter is thought to be made of particles that do not absorb, reflect, or emit light, making them invisible and detectable only through their gravitational effects, dark energy is believed to be responsible for the accelerated expansion of the universe. Particle physicists are on the hunt for particles that could constitute dark matter, using both underground detectors and space-based observatories to search for signs of these elusive particles, while cosmologists incorporate these findings into their models of the universe's overall structure and dynamics. Furthermore, the study of cosmic microwave background radiation, a relic of the Big Bang, offers a compelling example of how cosmology and particle physics intersect. This radiation provides a snapshot of the universe when it was just 380,000 years old, before stars and galaxies had formed. By analyzing its subtle temperature variations, scientists gain insights into the distribution of matter and the nature of the universe's early conditions, informing theories in both cosmology and particle physics about the fundamental forces and particles at play during the universe's formation. This interdisciplinary approach not only broadens our understanding of the universe, but also challenges and refines the theories in both fields. For example, discrepancies in measurements of the Hubble constant, which describes the rate at which the universe is expanding, suggest that there may be new physics at play not currently explained by the standard model of particle physics, or the lambda CDM model, the prevailing cosmological model. Such anomalies drive the quest for a more unified theory that can reconcile the laws governing the cosmos on the largest scales with those ruling the smallest particles. Building on the exploration of how cosmology intersects with particle physics, it's essential to delve into the fundamental forces of nature, which are the backbone of both the cosmos at large and the world of subatomic particles. These forces are like the universe's rulebook, dictating how everything, from galaxies to quarks, interacts. Understanding these forces provides insights into everything from the movement of planets to the stability of matter itself. Gravity is perhaps the most familiar force. It's the force that keeps our feet on the ground and governs the motion of planets, stars, and galaxies. Despite its universal presence, gravity is the weakest of the four forces. However, its influence spans immense distances, holding the universe together. The force of gravity between two objects is determined by their masses and the distance between them, as described by Isaac Newton's law of universal gravitation. Albert Einstein's theory of general relativity later refined our understanding of gravity, describing it as the curvature of space-time around masses. Electromagnetism is the force responsible for almost all the phenomena encountered in daily life above the nuclear scale. It acts between charged particles, such as protons and electrons, and is the force behind electricity, magnetism, and light. Electromagnetism is far stronger than gravity at the particle level and is essential for the structure of atoms, the chemical bonds between atoms, and the transmission of signals within our bodies. The strong nuclear force, also known as the strong interaction, is the strongest of the four forces but acts over a very short range. It binds protons and neutrons together in the nucleus of an atom. Without the strong force, atoms would not exist in their current form, as it overcomes the electromagnetic repulsion between positively charged protons within the nucleus. This force is also responsible for holding quarks together to form protons and neutrons, the components of atomic nuclei. The weak nuclear force, or weak interaction, is responsible for radioactive decay and certain types of nuclear reactions, such as those that power the sun. It acts over an even shorter range than the strong force and is pivotal in processes that change one type of subatomic particle into another, such as the transformation of a neutron into a proton, electron, and neutrino. This force plays a crucial role in the nuclear fusion reactions that fuel stars, and by extension, the synthesis of elements throughout the universe. These fundamental forces of nature are integral to the theories and experiments that bridge the vastness of cosmology with the intricacies of particle physics. Scientists strive to develop a unified theory that can cohesively explain all four forces within a single framework, a goal that has remained elusive. The quest for such a theory, often referred to as the theory of everything, continues to drive much of the research in physics, promising to unlock further mysteries of the universe. Let's delve into the particles that are considered the very building blocks of matter itself. These particles form the foundation of everything visible and tangible in our world, from the air we breathe to the stars in the night sky. The standard model of particle physics provides a framework that identifies the smallest constituents of matter, categorizing them into quarks, leptons, and the force carrier particles that mediate the fundamental forces. Quarks are incredibly tiny particles that combine to form protons and neutrons, the components of atomic nuclei. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Quarks are never found in isolation in nature due to a phenomenon known as color confinement. They are always bound together in groups of 2 or 3, forming particles known as mesons and baryons, respectively. Protons are made up of 2 up quarks and 1 down quark, while neutrons consist of 2 down quarks and 1 up quark. The properties and interactions of quarks are determined by the strong nuclear force, the most powerful of the 4 fundamental forces which keeps them locked together within the nucleus. Leptons are another category of fundamental particles, with the electron being the most well-known member. Like quarks, there are 6 flavors of leptons: the electron, muon, tau, and their corresponding neutrinos: electron neutrino, muon neutrino, and tau neutrino. Unlike quarks, leptons do not experience the strong nuclear force. Electrons orbit the nucleus of an atom, playing a crucial role in chemical reactions and electrical conductivity. Neutrinos are elusive particles that barely interact with matter, making them incredibly difficult to detect despite being produced in vast quantities by the sun and other nuclear processes. In addition to quarks and leptons, the standard model includes force carrier particles known as bosons, which mediate the 4 fundamental forces. Photons carry the electromagnetic force. Gluons mediate the strong force. W and Z bosons are responsible for the weak force, and the recently confirmed Higgs boson is associated with the Higgs field, which gives particles their mass. As we continue our journey, we venture into the realm of the Big Bang Theory, a pivotal concept that provides a compelling explanation for the origin of the universe. This theory is a cornerstone of modern cosmology and offers a window into the universe's earliest moments, suggesting that everything we observe today, from the smallest particles to the vastest galaxies, originated from a singular, incredibly dense and hot point, approximately 13.8 billion years ago. The Big Bang Theory proposes that the universe was once in an extremely hot and dense state that expanded rapidly. This expansion is not like an explosion of matter moving outward to fill an empty space, but rather the expansion of space itself. Imagine a balloon with dots on it representing galaxies. As the balloon inflates, the dots move away from each other, illustrating how galaxies move apart as the universe expands. Evidence supporting the Big Bang Theory is multifold and compelling. One of the key pieces of evidence is the cosmic microwave background radiation, CMB, a faint glow that permeates the universe, discovered accidentally by Arno Penzias and Robert Wilson in 1965. This radiation is the afterglow of the Big Bang, stretched to microwave frequencies by the expansion of the universe. Observations of the CMB provide a snapshot of the infant universe, allowing scientists to glean insights into its early conditions and composition. Another cornerstone of evidence comes from the observation of the redshift of galaxies, indicating that the universe is still expanding. This redshift occurs because the light from distant galaxies is stretched to longer, redder wavelengths as the space between us and the galaxies expands. Edwin Hubble was the first to observe this phenomenon in 1929. Edwin Hubble was the first to observe this phenomenon in 1929, providing direct evidence that the universe is not static, but dynamic and ever-expanding. Furthermore, the Big Bang theory explains the relative abundances of the lightest elements in the universe, hydrogen, helium, and lithium, observed today. These elements were formed during the first few minutes after the Big Bang in a process known as nucleosynthesis, and their proportions align closely with the predictions made by the theory. Despite its widespread acceptance and the strong evidence supporting it, the Big Bang theory is not without its unanswered questions and mysteries, such as the nature of dark matter and dark energy, which dominate the universe's total mass-energy content yet remain elusive. Moreover, the theory does not explain what preceded the Big Bang or the underlying cause of the initial expansion, leaving room for further theoretical and observational exploration. The Big Bang theory has revolutionized our understanding of the universe's origins, structure, and evolution. It paints a picture of a dynamic universe, born from a singular state of unimaginable density and heat, evolving over billions of years into the complex cosmos we observe today. In the immediate aftermath of the Big Bang, the universe was a hot, dense sea of energy. Conditions were so extreme that matter as we understand it, atoms, molecules, and their constituents, could not yet exist. Instead, the universe was filled with a quark-gluon plasma, a state in which quarks, the building blocks of protons and neutrons, and gluons, the particles responsible for the strong force that binds quarks together, moved freely in an ultra-hot, dense environment. This phase is akin to a soup of the universe's most fundamental ingredients, simmering in the aftermath of its explosive birth. As the universe expanded, it began to cool. Within the first microseconds, it cooled sufficiently for quarks to start binding together, forming protons and neutrons, the nuclei of future atoms. This period, known as the Hadron Epoch, marked the universe's first step toward the formation of matter as we recognize it. Further cooling allowed protons and neutrons to begin forming the universe's first nuclei during the nucleosynthesis phase, a few minutes after the Big Bang. Primarily, these were the simplest nuclei: hydrogen, which is a single proton; deuterium, a stable isotope of hydrogen with one neutron; helium, and trace amounts of lithium. The precise ratios of these light elements, predicted by the Big Bang nucleosynthesis theory, match closely with what we observe in the universe today, providing strong support for the Big Bang model. However, the universe remained too hot for electrons to bind to these nuclei to form neutral atoms. It wasn't until approximately 380,000 years after the Big Bang, during a period known as recombination, that the universe had cooled enough for electrons to combine with nuclei, creating the first neutral atoms. This event dramatically changed the universe's structure, allowing light to travel freely through space for the first time, leading to the release of the cosmic microwave background radiation, a snapshot of the infant universe that provides critical evidence for the Big Bang. The formation of the first neutral atoms marked the universe's transition from a plasma state to one that could eventually support stars, galaxies, and planets. Gravity began to pull matter together, leading to the formation of gas clouds that would become the nurseries for the first stars. These first stars synthesized heavier elements in their cores, contributing to the rich chemical diversity we observe in the universe today. The evidence for the Big Bang theory not only corroborates the notion that the universe originated from a singular, extremely dense and hot state, but also offers insights into the dynamics of the cosmos over billions of years. This evidence is crucial for both the scientific community and the broader public, offering a coherent narrative of cosmic evolution that is grounded in observation and analysis. The cosmic microwave background radiation, CMB, stands as a monumental pillar of evidence for the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB is a faint glow of light that fills the universe, remaining from the time shortly after the Big Bang. This radiation is the afterglow of the universe's infancy, cooled to microwave frequencies by the expansion of the universe over billions of years. Measurements of the CMB by satellites such as COBE, WMAP, and Planck have provided a detailed picture of the early universe, showing slight temperature fluctuations that correspond to regions of slightly different densities. These fluctuations were the seeds of all future structure, the galaxies, stars, and planets that fill the universe today. The expansion of the universe itself serves as direct evidence for the Big Bang. In the 1920s, Edwin Hubble made the groundbreaking discovery that galaxies are moving away from us in every direction, with their speed proportional to their distance from us. This observation, known as Hubble's law, suggests that the universe is expanding uniformly, implying that it was once far smaller, hotter, and denser, as the Big Bang theory predicts. The expansion of the universe is a dynamic testament to its explosive origin. The abundance of light elements provides another key piece of evidence. The Big Bang theory predicts the production of hydrogen, helium, and traces of lithium during the first few minutes after the Big Bang in a process known as primordial nuclear synthesis. Observations of the relative amounts of these elements in the universe closely match the predictions made by the Big Bang model, supporting the theory that the universe was once in a hot, dense state conducive to the formation of these elements. The large-scale structure of the universe, as observed through the distribution of galaxies and galaxy clusters, supports the Big Bang theory. Galaxies are not randomly distributed throughout the universe, but instead form a vast web of filaments and voids. This structure is consistent with the gravitational growth of initially small fluctuations in the density of the early universe predicted by the Big Bang theory. Continuing on our journey, we delve into the concept of quantum fluctuations, a phenomenon deeply rooted in the quantum realm that plays a pivotal role in the fabric of the cosmos. Quantum fluctuations are temporary changes in the amount of energy in a point in space, as dictated by Werner Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like position and momentum, cannot both be precisely measured at the same time. This principle is a cornerstone of quantum mechanics and introduces the concept of inherent uncertainty at the quantum level. In the vacuum of space, what we might think of as empty quantum fluctuations occur spontaneously, with particles and antiparticles popping into and out of existence. These particles, known as virtual particles, exist for an incredibly short period of time before annihilating each other. Despite their transient nature, they have real effects and can influence the behavior of other particles. For instance, quantum fluctuations are believed to be responsible for the slight shifts in the energy levels of electrons in atoms, an effect observed and verified through experiments. Quantum fluctuations are not just a curious aspect of quantum mechanics. They are thought to have played a critical role in the formation of the universe as we know it. During the period of cosmic inflation, a brief period of rapid expansion that occurred a fraction of a second after the Big Bang, these quantum fluctuations were stretched to macroscopic scales. This process magnified the tiny fluctuations in the density of the universe, leading to the large-scale structures we observe today, such as galaxies and galaxy clusters. The patterns imprinted in the cosmic microwave background radiation are a direct result of these quantum fluctuations, offering a glimpse into the quantum origins of the universe. At the heart of quantum fluctuations is the Heisenberg uncertainty principle, which posits that certain pairs of physical properties, like position and momentum, cannot both be known exactly at the same time. This principle suggests that even what we consider a vacuum is not truly empty, but teems with virtual particles popping into and out of existence. These particles are called virtual because they cannot be directly observed. They exist temporarily, borrowing energy from the vacuum to appear for a fleeting moment before annihilating each other and returning the borrowed energy. However, under certain conditions, quantum fluctuations can lead to the creation of real particles. One such scenario occurs near the event horizon of a black hole, a phenomenon known as Hawking radiation. Stephen Hawking proposed that quantum fluctuations at the edge of a black hole could result in the creation of particle-antiparticle pairs, with one particle falling into the black hole and the other escaping into space. This process effectively leads to the creation of real particles from the vacuum, with the black hole losing mass over time as a result of this radiation. Another context in which quantum fluctuations lead to particle creation is during the period of cosmic inflation, a theory suggesting that the universe underwent a rapid expansion shortly after the Big Bang. During inflation, quantum fluctuations were stretched to macroscopic scales, magnifying their effects. These fluctuations in the density of the early universe served as the seeds for the formation of all large-scale structures we observe today, such as galaxies and galaxy clusters. The magnification of quantum fluctuations during inflation implies that the virtual particles could freeze into real particles, contributing to the matter content of the universe. This process of particle creation from quantum fluctuations underscores the interconnectedness of quantum mechanics and cosmology, revealing the quantum underpinnings of cosmic evolution. It illustrates how the universe at its largest scales is influenced by phenomena occurring at the smallest scales, blurring the lines between the void and the tangible, between nothingness and existence. Diving deeper into the quantum realm, the role of energy in particle formation is a critical aspect that bridges the gap between the ephemeral nature of quantum fluctuations and the tangible reality of the universe. Energy plays a pivotal role in the birth of particles, acting as the catalyst that transforms the potential within quantum fluctuations into the material constituents of the cosmos. This process is rooted in one of the most famous equations in physics, E=mc², proposed by Albert Einstein, which posits that energy, E, and mass, m, are interchangeable, with c being the speed of light. This fundamental principle underscores the deep connection between energy and the creation of particles, illustrating how fluctuations in the quantum vacuum can give rise to matter. In the vacuum of space, what appears to be empty is in fact a seething cauldron of energy due to quantum fluctuations. These fluctuations represent temporary changes in the amount of energy at a point in space, allowing for the creation of particle-antiparticle pairs. Although these pairs typically annihilate each other almost instantaneously, returning the borrowed energy to the vacuum under certain conditions, they can become real particles. The conversion of energy into particles is a cornerstone of our understanding of the early universe and the processes that filled it with matter. For instance, in the incredibly high energy conditions that followed the Big Bang, the universe was a hot, dense soup of energy. As the universe expanded and cooled, some of this energy condensed into particles, following the principles laid out by Einstein's equation. The early universe went through various phases, including the electroweak epoch and the quark epoch, during which the fundamental forces of nature separated and the building blocks of matter formed and coalesced into the protons and neutrons that make up atomic nuclei today. Energy not only facilitates the creation of particles, but also influences their interactions and the structures they form. For example, the energy released during nuclear fusion processes in the hearts of stars is responsible for synthesizing the heavier elements essential for life, from carbon to iron. This transformative power of energy, from igniting stars to forging elements, highlights its fundamental role in shaping the cosmos. Navigating from the pivotal role of energy in particle formation, we find ourselves at the doorstep of another fundamental concept we talked about earlier, the Heisenberg uncertainty principle. This principle is not just a mathematical curiosity, it's a window into the inherent fuzziness of the quantum world and has direct implications for the creation of particles from seemingly empty space. The uncertainty principle, introduced by Werner Heisenberg in 1927, states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This inherent uncertainty is not due to experimental imperfections, but is a fundamental property of the universe at the quantum level. The uncertainty principle is intimately related to particle creation, particularly in the context of quantum fluctuations in the vacuum of space. According to quantum field theory, the vacuum isn't empty but teems with virtual particles that continually pop into and out of existence. These particles are termed virtual because they exist temporarily, borrowing energy from the vacuum due to the allowances made by the uncertainty principle. The principle permits these fluctuations by allowing a temporary violation of energy conservation with the stipulation that the borrowed energy must be paid back quickly, thus preventing any violation from being directly observed. This temporary borrowing of energy makes it possible for particle-antiparticle pairs to form spontaneously. Although these pairs usually annihilate each other almost immediately, returning their borrowed energy to the vacuum, their brief existence is a direct consequence of the uncertainty inherent in their positions and momenta. Horizon of a black hole, or during the rapid expansion of the early universe, these virtual particles can be separated and become real, observable particles. This process of particle creation from the vacuum, facilitated by the uncertainty principle, highlights the principle's crucial role in the dynamics of the quantum world and the fabric of the cosmos. In the initial fraction of a second after the Big Bang, the universe was too hot and dense for any particles or atoms to exist. It was filled with a quark-gluon plasma, a state of matter in which quarks, fundamental particles that later formed protons and neutrons, were not confined within atomic nuclei, but were free in a soup of gluons, particles that mediate the strong force holding quarks together. As the universe expanded and cooled, it reached a temperature where quarks could coalesce to form protons and neutrons, the building blocks of atomic nuclei. This epoch, known as the Hadron epoch, occurred within the first microsecond to 1 second after the Big Bang. The formation of protons and neutrons marked a pivotal moment in the early universe, setting the stage for the creation of more complex forms of matter. Following the Hadron epoch, the universe continued to cool, leading to the Lepton epoch, which lasted from about 1 second to a few minutes post-Big Bang. During this period, leptons, such as electrons, were the dominant form of matter. The universe was still too hot for protons and neutrons to combine into nuclei with these electrons. The most critical event related to particle formation came next: nucleosynthesis, a process that occurred within the first few minutes after the Big Bang. During this period, the universe had cooled sufficiently for protons and neutrons to begin combining to form the nuclei of the simplest elements: hydrogen, helium, and trace amounts of lithium and beryllium. This primordial nucleosynthesis was responsible for creating most of the helium in the universe, alongside the hydrogen that did not bind into helium nuclei. It's important to note that these were not yet complete atoms in the way we think of them today, with electrons orbiting a nucleus. The universe remained too hot for electrons to be captured into orbits around nuclei, forming neutral atoms. This formation of neutral atoms, a process known as recombination, would not occur until approximately 380,000 years after the Big Bang, leading to the decoupling of matter and radiation, and the release of the cosmic microwave background radiation, the afterglow of the Big Bang, which provides us with a snapshot of the universe at that time. Now, let's venture further into the fascinating epoch when the fundamental forces of nature began to delineate and define the evolving cosmos. This narrative of separation is a cornerstone in understanding the universe's intricate tapestry, from its most nascent moments to the richly structured expanse we observe today. Initially, in the universe's first moments, all forces were unified in a singular force, a testament to the extreme conditions of temperature and density that pervaded the cosmos. As the universe expanded and cooled, this primordial unity fractured in a series of symmetry-breaking events, leading to the distinct forces we recognize today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The first to separate was gravity, emerging as a distinct force as the universe cooled from its unfathomably hot and dense state. This separation is hypothesized to have occurred just a fraction of a second after the Big Bang, marking the universe's first step towards the complex force interactions that govern it now. Gravity's decoupling set the stage for the cosmos's large-scale structure, guiding the formation of galaxies, stars, and planets, shaping the universe's very fabric. Following gravity's separation, the grand unified force, encapsulating the electromagnetic, strong, and weak nuclear forces, persisted in its unified state until the universe further cooled. As the temperature dropped to a critical point, the strong nuclear force, responsible for binding quarks within protons and neutrons and keeping atomic nuclei intact, distinguished itself from the electroweak force, a combined form of the electromagnetic and weak nuclear forces. This separation, occurring roughly 10 circumflex 36 to 10 circumflex 32 seconds after the Big Bang during the cosmic inflation epoch, laid the groundwork for the formation of the universe's first particles. The electroweak force continued to govern the universe's energetic landscape until it too underwent symmetry breaking. This event, taking place approximately 10 circumflex 12 seconds after the Big Bang, saw the electroweak force split into the electromagnetic force mediated by photons and the weak nuclear force responsible for radioactive decay and nuclear fusion processes in stars. This delineation finalized the roster of fundamental forces, setting the stage for the universe to cool further, allowing for the formation of more complex particles and, eventually, atoms. The separation of the fundamental forces during the universe's infancy was a pivotal series of events that enabled the diversity of matter and structures observed in the cosmos today. Moving on from the pivotal moments when the fundamental forces of nature began their gradual separation, we delve into the significance of the electroweak epoch, a defining period in the universe's evolution. This epoch represents a critical phase shortly after the Big Bang, during which the electromagnetic and weak nuclear forces, two of the four fundamental forces, were unified as a single force known as the electroweak force. The electroweak epoch occurred approximately between 10 circumflex 12 seconds and 10 circumflex 6 seconds after the Big Bang, a time when the universe was cooling down from its initially hot and dense state, yet still incredibly energetic and dynamic. The significance of the electroweak epoch lies in its role in shaping the early universe and setting the stage for the formation of matter as we know it. During this epoch, the universe was filled with a hot, dense plasma of quarks, leptons, and their antiparticles, along with the electroweak bosons that mediated the unified force. As the universe expanded and cooled, it reached a critical temperature that allowed the electroweak force to undergo a symmetry-breaking event. This event led to the differentiation of the electromagnetic force, mediated by photons, from the weak nuclear force, mediated by W and Z bosons. This separation was a fundamental step in the universe's maturation, allowing for a diversity of interactions that would eventually lead to the formation of atoms and, consequently, the structure of the cosmos. The electroweak epoch has profound implications for our understanding of particle physics and the Standard Model. The Higgs mechanism, predicted by the Higgs field's presence, played a crucial role during this epoch. The interaction of particles with the Higgs field endowed them with mass, a process central to the symmetry-breaking event that distinguished the electromagnetic and weak nuclear forces. The discovery of the Higgs boson in 2012, a particle associated with the Higgs field, provided a key piece of evidence supporting the theoretical framework describing the electroweak force and its significance. Quarks, the fundamental constituents of matter, are subject to the strong nuclear force, one of the four fundamental forces that became distinct in the earlier phases of the universe's evolution. This force, also known as the strong interaction, is remarkably powerful, but its influence extends over only a very short range. In the universe's nascent moments, it acted as the glue that bound quarks together in groups of 3 to form baryons, which include protons and neutrons, the building blocks of atomic nuclei. The process began when the universe cooled sufficiently for the strong force to overcome the kinetic energy that had previously kept quarks apart. In this cooler, yet still incredibly hot environment, quarks started to interact more closely, forming pairs known as quark-antiquark pairs, and triplets that would evolve into protons and neutrons. A proton is composed of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The specific combination of quarks determines the properties of the particle, including its charge. Protons carry a positive charge due to their quark composition, whereas neutrons are neutral. This phase of the universe's development was not just about the formation of these particles, but also about the transition from a state where quarks could move freely, a quark-gluon plasma, to a state where they were locked within protons and neutrons. This locking mechanism is crucial for the stability of matter as we know it. Without it, the complex structures that make up the universe, from atoms to galaxies, could not exist. The hadronization of quarks into protons and neutrons set the stage for the next phase of cosmic evolution, the nucleosynthesis era, when the first atomic nuclei formed. These early steps of matter coalescing from the fundamental forces and particles shaped by the conditions of the early universe are central to our understanding of cosmic history and the very matter that makes up the world around us. As the universe continued to expand and cool after the formation of protons and neutrons, it reached a temperature conducive to the fusion of these particles. This epoch, occurring roughly 3 minutes after the Big Bang, was when conditions were just right for the nuclear forces to overcome the repulsive electromagnetic forces between positively charged protons, allowing them to come together with neutrons to form the nuclei of the simplest elements. Primarily, hydrogen nuclei, protons, fuse to form helium, along with trace amounts of deuterium, heavy hydrogen, tritium, a radioactive form of hydrogen, and very small quantities of lithium and beryllium. The process of nucleosynthesis is critical for several reasons. First, it set the initial abundance of the light elements in the universe. The proportions of hydrogen and helium created during this time have been measured in the present universe and are found to be in remarkable agreement with the predictions made by the Big Bang theory, serving as a key piece of evidence for the theory itself. Second, these primordial nucleosynthesis events laid the groundwork for the formation of stars. Stars, through their own cycles of nuclear fusion, would later forge the heavier elements essential for life and the complex structures of the universe. The significance of nucleosynthesis extends beyond the mere creation of atomic nuclei. It marks the universe's transition from a place of simple particles and forces to a complex tapestry of matter. It was during this period that the universe took its first steps toward chemical diversity, setting the stage for the long cosmic evolution that would eventually lead to the formation of planets, life, and the vast array of celestial phenomena that fill the cosmos. On our journey for answers, we arrive at the next pivotal chapter in the universe's early history, the formation of the first atoms. This milestone event, occurring around 380,000 years after the Big Bang, marked the universe's cooling to a point where electrons could bind with nuclei to form neutral atoms, a period known as recombination. The backdrop for this monumental shift was a universe expanding and cooling from its initial state of extreme heat and density, setting the stage for the birth of atomic matter as we know it. As the universe cooled, the protons and neutrons that had formed from quarks began to interact through nuclear fusion, creating the first simple nuclei during the nucleosynthesis phase. This primarily led to the formation of hydrogen, which is simply a single proton, and helium nuclei, along with trace amounts of deuterium, heavy hydrogen, and lithium. These light elements formed the universe's initial chemical abundance, setting a primordial stage rich in hydrogen and helium, the simplest and most abundant elements in the cosmos. However, the universe remained too hot for electrons to remain bound to these nuclei. They existed in a state of free electron plasma, scattering photons and keeping the universe opaque. As the universe continued to expand and cool, it eventually reached a temperature where the energy of the photons was no longer sufficient to ionize hydrogen. At this juncture, electrons began to combine with hydrogen and helium nuclei to form the first stable atoms. This recombination process drastically reduced the scattering of photons, allowing the universe to become transparent for the first time. The photons released at this point form the cosmic microwave background radiation, a relic radiation that provides a snapshot of the universe at the moment of recombination. The formation of the first atoms was a turning point in the cosmic narrative, paving the way for the universe's transition from a hot, dense state to a cooler, structured one, capable of supporting complex structures such as stars and galaxies. It signified the end of the universe's dark ages, a time before the first stars ignited, and set the stage for the gravitational collapse of matter into the first stars and galaxies. These stars would further enrich the cosmos with heavier elements through stellar nucleosynthesis, seeding the universe with the ingredients necessary for planets and life. Nucleosynthesis, the process by which the natural abundances of the chemical elements within stars were formed, played a crucial role in creating the diversity of elements that we observe in the universe today. Following the formation of the first atoms, the universe was primarily composed of hydrogen and helium, the simplest and most abundant elements. However, the complex and varied world around us, from the air we breathe to the materials that make up the Earth, and even the components of our own bodies, requires a much broader array of elements. Nucleosynthesis provided the processes necessary to forge these elements, acting as the cosmic furnace that transformed the primordial simplicity of the early universe into a rich tapestry of chemical diversity. The process of nucleosynthesis occurred in several stages and environments, starting with the Big Bang itself. Big Bang nucleosynthesis, occurring within the first minutes of the universe, produced the lightest elements, including hydrogen, helium, and trace amounts of lithium and beryllium. However, this process could not account for the creation of heavier elements that are essential for life and the structure of the cosmos. The next phase of nucleosynthesis took place within stars. Stars are the universe's factories for element production, transforming lighter elements into heavier ones through nuclear fusion in their cores. In the life cycle of a star, hydrogen nuclei fuse to form helium in a process known as hydrogen burning. As stars age and their cores heat up, they can fuse helium into carbon, and in more massive stars the process continues, forming elements up to iron through successive stages of nuclear burning, such as carbon burning, neon burning, oxygen burning, and silicon burning. However, the creation of elements heavier than iron requires a different set of processes, as these elements cannot be formed through fusion in stellar cores under normal circumstances due to their energy requirements. Instead, processes such as the R process, rapid neutron capture, and the S process, slow neutron capture, come into play, primarily during supernova explosions and in the outer shells of asymptotic giant branch, AGB stars. Supernovae, the cataclysmic explosions that mark the death of massive stars, provide the necessary conditions for the R process, where a dense flux of neutrons is absorbed by atomic nuclei, leading to the creation of many of the heavier elements in the periodic table. The S process occurs in the more serene environs of AGB stars, where neutrons are captured more slowly, allowing for the creation of elements like barium and lead. The diverse elements forged by nucleosynthesis are eventually spread throughout the galaxy by stellar winds and supernova explosions, seeding interstellar clouds with the materials needed for the next generation of stars, planets, and eventually, life. This cycle of star birth, nucleosynthesis, and death, followed by the reformation of new stellar systems, has enriched the universe with a complex chemistry over billions of years. Particle accelerators are sophisticated machines that propel charged particles, such as protons or electrons, to high speeds and smash them together or against targets, generating conditions that mimic those just after the Big Bang. These groundbreaking tools allow scientists to investigate the fundamental properties of matter and the forces that govern the interactions between particles. By accelerating particles to nearly the speed of light and then colliding them, particle accelerators enable researchers to break down atomic components into their constituent parts, revealing particles and phenomena not observable under normal conditions. The workings of a particle accelerator involve using electric fields to accelerate particles and magnetic fields to steer and focus them along a specified path, which can be circular, as in synchrotrons and storage rings, or linear, as in linear accelerators, LINACs. When these high-energy particles collide, they produce a variety of new particles, allowing scientists to study the rules of particle physics in environments of extreme energy densities, similar to those that existed just after the Big Bang. There are several types of particle accelerators, each serving different purposes in the field of research and beyond. For instance, the Large Hadron Collider, LHC, at CERN near Geneva, Switzerland, is the world's largest and most powerful particle accelerator, designed to probe deeper into the mysteries of the universe, such as the properties of the Higgs boson, dark matter, and other fundamental questions about the nature of reality. Beyond their fundamental scientific applications, particle accelerators have practical uses in various fields, including medicine, where they are used for cancer treatment through radiation therapy, and in producing isotopes for medical diagnostics, in industry for materials processing and the creation of semiconductors, and in art and archaeology for analyzing paintings and artifacts without damaging them. The development and operation of particle accelerators are feats of engineering and physics, combining advanced technologies in superconducting magnets, vacuum systems, and particle detection to explore the frontiers of human knowledge. These machines are not just tools for discovery, but are also catalysts for technological innovation, driving advances in numerous fields and contributing to the technological infrastructure of society. Particle accelerators have been instrumental in advancing our understanding of the fundamental aspects of the universe, leading to numerous significant discoveries that have shaped modern physics. These machines, by propelling particles to high velocities and facilitating their collisions, have allowed scientists to probe the deepest secrets of the universe, revealing the existence of particles and forces that constitute the fabric of everything around us. One of the most groundbreaking discoveries made with the aid of particle accelerators was the identification of the Higgs boson. In 2012, scientists at CERN's Large Hadron Collider, LHC, announced they had detected a particle consistent with the Higgs boson, often referred to as the God particle. This particle, predicted by the Standard Model of particle physics, is fundamental to understanding why other particles have mass. The discovery of the Higgs boson was a monumental moment in the field of particle physics, confirming a key pillar of the Standard Model and contributing to the Nobel Prize in Physics for François Englert and Peter Higgs in 2013. Particle accelerators have also been pivotal in confirming the existence of quarks, the building blocks of protons and neutrons. In the late 1960s and early 1970s, experiments conducted at the Stanford Linear Accelerator Center, SLAC, provided the first direct evidence of quarks, supporting the quark model proposed by physicists Murray Gell-Mann and George Zweig in the 1960s. This was a significant step forward in our understanding of the structure of matter, establishing quarks as fundamental constituents of matter. Furthermore, accelerators have facilitated the study of antimatter, particles that are identical to matter particles but with opposite charge. Experiments at CERN and other facilities have allowed physicists to create, trap, and study antimatter particles, such as antihydrogen. These studies are crucial for testing the fundamental symmetries of the universe and for understanding why the universe is composed mainly of matter, despite the Big Bang theory predicting equal amounts of matter and antimatter. Particle accelerators have also enabled the discovery of a plethora of subatomic particles, including W and Z bosons, which mediate the weak nuclear force responsible for radioactive decay. The discovery of these particles in the 1980s at CERN provided critical proof of the electroweak theory, which unifies the electromagnetic and weak forces, one of the key achievements in efforts to develop a unified theory of fundamental forces. Beyond fundamental discoveries, particle accelerators have contributed to advancements in medical treatments, such as cancer therapy, through particle beams, and in the development of technologies like the World Wide Web, initially created at CERN to facilitate information sharing among scientists. Now, how do these experiments in particle physics validate theoretical predictions? The interplay between theory and experiment in particle physics involves several key steps. Theoretical physicists develop models based on mathematical principles to explain the properties and behaviors of particles and the forces that govern their interactions. These models often make precise predictions about the outcomes of certain interactions or the existence of previously unobserved particles. To test these predictions, experimental physicists design and conduct experiments using particle accelerators. These machines accelerate particles to high energies and then collide them, creating conditions that allow for the observation of phenomena that are not accessible under normal circumstances. The detectors surrounding the collision points capture and record the particles produced in these collisions, and sophisticated data analysis techniques are employed to interpret the results. A significant aspect of validating theoretical predictions is the ability to reproduce experimental results. In particle physics, this often means that multiple experiments, sometimes at different facilities around the world, must observe the same phenomena under similar conditions. This replication of results adds credibility to the findings and helps to confirm that they are not statistical anomalies or artifacts of the experimental setup. The Standard Model of particle physics is a theory that describes 3 of the 4 known fundamental forces in the universe: the electromagnetic, weak, and strong nuclear forces, and classifies all known elementary particles. It is a cornerstone of modern physics and represents the best understanding scientists have of how the fundamental constituents of the universe behave and interact. The model has been developed over several decades, starting in the mid-20th century through the collaborative efforts of physicists around the world. At its core, the Standard Model is built on the foundation of quantum mechanics and special relativity, incorporating both into a unified framework known as quantum field theory. The model categorizes elementary particles into 2 main groups: fermions and bosons. Fermions are the building blocks of matter, divided into quarks and leptons, including particles like electrons, and the quarks that make up protons and neutrons. Bosons are force carrier particles that mediate the fundamental forces. For instance, photons carry the electromagnetic force, while gluons are responsible for the strong force. A significant triumph of the Standard Model was the prediction and subsequent discovery of the Higgs boson, a particle that provides mass to other particles through the Higgs mechanism. This discovery at the Large Hadron Collider in 2012 filled a crucial gap in the model and was hailed as one of the most significant achievements in physics, confirming the existence of the Higgs field and its associated particle. Despite its successes, the Standard Model is not complete. It does not incorporate the 4th fundamental force, gravity, described by general relativity, nor does it account for the dark matter and dark energy that appear to constitute most of the universe's mass energy content. Additionally, the model's inability to incorporate the gravitational force or predict the masses of elementary particles suggests that it is a part of a more comprehensive theory yet to be discovered. While the Standard Model of particle physics stands as a remarkably successful theoretical framework, it also has its limitations, marking areas where our current understanding of the universe is incomplete. These limitations not only highlight the boundaries of the model's applicability, but also point toward new physics beyond what we currently know, guiding researchers in their quest to uncover a more comprehensive theory of the fundamental forces and particles. One of the most significant limitations of the Standard Model is its inability to incorporate gravity. Gravity, described by Einstein's theory of general relativity, is a fundamental force that governs the structure and dynamics of the cosmos on the largest scales, from the orbits of planets to the evolution of galaxies and the universe itself. However, the Standard Model is based on the framework of quantum field theory, which does not naturally include gravity. This discrepancy between the theories of the very large, general relativity, and the very small, quantum mechanics, remains one of the most profound challenges in physics. Another limitation is the Standard Model's silence on the nature of dark matter and dark energy. Observations of the universe suggest that about 85% of its matter content is dark matter, which does not emit, absorb, or reflect light, and is detectable only through its gravitational effects. Dark energy, contributing to about 68% of the total energy content of the universe, is thought to be responsible for its accelerating expansion. The Standard Model, however, does not predict the existence of dark matter particles, nor does it account for the properties of dark energy, leaving a significant portion of the universe unexplained. The Standard Model also cannot explain the matter-antimatter asymmetry observed in the universe. According to the model, the Big Bang should have produced equal amounts of matter and antimatter, which would annihilate each other, leaving behind a universe filled with radiation. However, the observable universe is dominated by matter, suggesting that processes not accounted for in the Standard Model must have given matter an edge over antimatter. The Standard Model does not provide a satisfactory explanation for the masses of neutrinos. Initially, the model assumed that neutrinos were massless, but experiments have shown that they have a small mass. This discovery has necessitated revisions to the model, but has also opened up new questions about the origins of neutrino mass and their role in the universe. The Standard Model is a patchwork of particles and forces without a unifying principle that could explain why this particular set of particles and forces exists. The search for a theory of everything that would unify all fundamental forces, including gravity, and offer a more fundamental understanding of the particles themselves, remains a major goal of theoretical physics. Dark matter and dark energy are two of the most profound mysteries in modern cosmology, a universe that are invisible and undetectable by traditional means, but whose presence is inferred from their gravitational effects and the impact on the universe's expansion. Together, they compose about 95% of the total mass energy content of the universe, with dark matter accounting for approximately 27% and dark energy for about 68%, leaving ordinary matter, everything we can see and interact with, making up just a small fraction. Dark matter is a form of matter that does not emit, absorb, or reflect light, making it completely invisible to electromagnetic radiation and, thus, extremely difficult to detect directly. Its existence was first posited in the 1930s by Swiss astronomer Fritz Zwicky, who observed that galaxies within clusters were moving at speeds that implied the presence of much more mass than could be accounted for by the visible matter alone. Since then, further evidence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation has supported the existence of dark matter. Despite being invisible, dark matter exerts gravitational forces, influencing the structure and formation of galaxies and galaxy clusters. It acts as a cosmic scaffold around which visible matter congregates and forms into the large-scale structures observed in the universe. Dark energy, on the other hand, is a mysterious force that is driving the accelerated expansion of the universe. The discovery of dark energy in the late 1990s was a significant surprise to astronomers who had expected that the universe's expansion might be slowing down due to the gravitational attraction of its contents. Instead, observations of distant supernovae revealed that galaxies are moving away from each other at an accelerating rate. Dark energy is thought to be a property of space itself, evenly distributed throughout the universe and not diluting as space expands. Its nature is even less understood than that of dark matter, and it poses a fundamental challenge to our understanding of the laws of physics, as it does not fit neatly into the Standard Model of particle physics or the theory of general relativity. Dark matter, which constitutes about 27% of the universe, interacts with ordinary matter through gravity. It does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. dark matter's presence is inferred from its gravitational pull on galaxies and galaxy clusters, influencing their rotation rates and distribution. This invisible matter acts as a cosmic scaffold, providing the gravitational framework necessary for galaxies to form and cluster together. During the early universe, dark matter's gravitational pull helped to amplify the slight irregularities left by quantum fluctuations, leading to the formation of large-scale structures like galaxies and clusters of galaxies. These structures created the potential wells within which ordinary matter could gather and cool, leading to star formation and the subsequent synthesis of heavier elements through nucleosynthesis in stars. Dark energy, on the other hand, accounts for approximately 68% of the universe and is thought to be responsible for its accelerated expansion. Unlike dark matter, dark energy does not cluster but is uniformly distributed across space, exerting a repulsive force that counteracts gravity. The exact nature of dark energy remains one of the biggest mysteries in physics, but its effect on the universe's expansion rate has critical implications for particle formation and the evolution of the cosmos. The accelerated expansion affects the density and temperature of the universe over time, influencing the rate at which structures form and evolve. This expansion impacts the cooling of the universe and the regions where particles can come together to form atoms, molecules, and eventually the stars and galaxies. Supersymmetry, often abbreviated as SUSY, is a theoretical framework in particle physics that proposes a type of symmetry between two fundamental classes of particles: bosons, which carry forces, and fermions, which make up matter. According to supersymmetry, for every boson in the Standard Model, there exists a corresponding fermion partner, and vice versa, that has not yet been observed. These partner particles are known as superpartners, with names that mirror their Standard Model counterparts, but with prefixes or suffixes added, such as squarks for superpartners of quarks, and selectrons for superpartners of electrons. The allure of supersymmetry lies in its potential to address several unresolved issues within the Standard Model of particle physics and cosmology. One of the most significant challenges it aims to solve is the hierarchy problem, which concerns the vast difference in strength between the gravitational force and the other fundamental forces. Supersymmetry suggests that new symmetries in the laws of physics can stabilize the mass of the Higgs boson against quantum corrections that could otherwise make it much heavier, thus providing a natural explanation for the weak scale and the stability of the Higgs boson's mass. Moreover, supersymmetry is a leading candidate for explaining dark matter, a mysterious substance that makes up about 27% of the universe but does not emit, absorb, or reflect light. Supersymmetric particles, particularly the lightest supersymmetric particle, LSP, are stable, electrically neutral, and only weakly interacting, making them excellent candidates for dark matter. If these particles exist, they could account for the gravitational effects attributed to dark matter in galaxies and clusters of galaxies. Despite its elegant theoretical foundation and the compelling solutions it offers to some of physics' most perplexing questions, direct evidence for supersymmetry has yet to be found. Particle accelerators, such as the Large Hadron Collider, LHC, at CERN, have conducted extensive searches for superpartners of known particles. However, as of my last update, these efforts have not yet resulted in the discovery of supersymmetric particles, leading to increased constraints on supersymmetric models and pushing the predicted masses of superpartners to higher values outside the reach of current experiments. Now, are there theories that propose particles beyond the Standard Model? There are several compelling theories that propose the existence of particles beyond those described in the Standard Model of particle physics. These theories aim to address the limitations and unanswered questions left by the Standard Model, such as the nature of dark matter, the hierarchy problem, and the unification of forces. Among the most prominent of these theories are supersymmetry, SUSY, string theory, and theories involving extra dimensions. Supersymmetry, as mentioned earlier, extends the standard model by introducing a superpartner for each particle, effectively doubling the particle zoo. These superpartners, which have not yet been observed, could help explain the dark matter mystery and offer a solution to the hierarchy problem by stabilizing the mass of the Higgs boson. Supersymmetry predicts a range of new particles, such as the gluino, the superpartner of the gluon, and the gravitino, the superpartner of the graviton, a hypothetical particle associated with gravity. String theory, another leading candidate for extending our understanding of the fundamental constituents of the universe, proposes that the elementary particles are not point-like dots, but rather tiny vibrating strings. The vibrational modes of these strings correspond to different particles, with their vibration patterns determining the particle's properties. String theory inherently includes supersymmetry and predicts the existence of many new particles, including those responsible for gravity, potentially offering a way to unify all fundamental forces. It also suggests the existence of additional spatial dimensions beyond the familiar three. Theories involving extra dimensions, such as those proposed in various string theory formulations and in approaches like the brain world scenario, suggest that our universe might have more than the three spatial dimensions we experience. These extra dimensions could be compactified and hidden on scales too small for current experiments to detect directly. Particles could propagate through these extra dimensions, potentially explaining why gravity is so much weaker than the other fundamental forces, and suggesting the existence of particles associated with these dimensions. Another approach includes theories of grand unification, which aim to unify the electromagnetic, weak and strong nuclear forces into a single force by introducing additional symmetry groups. These theories predict the existence of new particles, such as heavy gauge bosons, which could mediate transitions between quarks and leptons, changing one type of particle into another. While these theories are mathematically elegant and offer exciting solutions to the standard model's shortcomings, direct experimental evidence for particles beyond the standard model remains elusive. Particle accelerators, such as the Large Hadron Collider, are at the forefront of searching for these hypothetical particles. Discovering them would not only validate these theories, but also dramatically change our understanding of the universe's fundamental structure and forces. Gravity, the weakest yet most far-reaching of the four fundamental forces, exerts a profound influence on the formation of particles, shaping the cosmos from the smallest scales to the vastness of galactic structures. While its effects are subtle in the realm of particle physics, gravity's role becomes increasingly significant as we consider the broader context of the universe's evolution and the formation of structures within it. Gravity's most direct impact on particle formation can be seen in the process of star formation. As vast clouds of gas and dust in galaxies collapse under their own gravity, they create dense regions where the conditions become favorable for nuclear fusion. The intense pressure and temperature in the cores of these nascent stars initiate the fusion of hydrogen atoms into helium, releasing energy in the process. This fusion, the heart of stellar nuclear synthesis, generates the heavier elements essential for life and the diversity of the chemical elements found throughout the universe. Gravity is instrumental in the formation of black holes, regions of space-time where gravitational forces are so strong that nothing, not even light, can escape. In the extreme conditions near a black hole's event horizon, theoretical processes such as Hawking radiation predict the creation of particle-antiparticle pairs from the vacuum of space itself. While one particle falls into the black hole, the other escapes, suggesting a fascinating interplay between gravity and quantum mechanics that could influence particle formation. On a cosmological scale, gravity's role in particle formation extends to the very structure of the universe. The distribution of matter, from the filamentary structures that make up the cosmic web to the formation of galaxies and galaxy clusters, is governed by gravitational attraction. This distribution, in turn, determines the regions where particles can come together to form stars, planets, and other astronomical bodies. While gravity's direct influence on the behavior of individual particles is overshadowed by the stronger electromagnetic and nuclear forces at small scales, its cumulative effect over cosmic timescales and distances is crucial for understanding the universe's evolution. The formation of particles, stars, and galaxies, and the very structure of the cosmos are all testament to gravity's foundational role in shaping the universe from its earliest moments to the present day. The theory of inflation is a pivotal concept in cosmology that addresses some of the most fundamental questions about the early universe. Proposed in the early 1980s by physicists including Alan Guth and Andre Linde, inflation posits that the universe underwent an exponential expansion in the first fractions of a second after the Big Bang. This rapid expansion, much faster than the speed of light, stretched the size of the universe by many orders of magnitude in a blink of an eye. Inflation was introduced to solve several problems inherent in the Big Bang theory as it stood at the time. One of these was the horizon problem, which questions how parts of the universe that are now widely separated could have come to be at the same temperature when light hasn't had enough time to travel between them since the beginning of the universe. Inflation explains this by proposing that these regions were once close together before being driven apart by the swift expansion, allowing them to come into thermal equilibrium before being separated beyond the horizon of causal connection. Another issue addressed by inflation is the flatness problem. Observations suggest that the universe is remarkably flat, meaning it conforms to the geometry described by Euclidean geometry over large scales, requiring a fine-tuning of initial conditions if the universe expanded at a steady rate from the Big Bang. Inflation elegantly solves this by diluting any curvature in the early universe's fabric, leading to a universe that appears flat on large scales, as observed. Inflation also provides an explanation for the origin of the large-scale structure of the universe. The theory predicts that tiny quantum fluctuations in the early universe were stretched to astronomical scales by the inflationary expansion. These fluctuations then served as the seeds for the growth of structure in the universe, such as galaxies and galaxy clusters, through gravitational attraction. The theory of inflation is supported by observations of the cosmic microwave background radiation, the afterglow of the Big Bang, which shows patterns of slight temperature variations consistent with the predictions of inflation. These observations have solidified inflation's role as a cornerstone of our understanding of the early universe, despite it being a theory that pushes the boundaries of current physics. While the theory of inflation has greatly enhanced our understanding of the cosmos's early moments, it also raises new questions, such as what caused inflation to start and what stopped it. Various models of inflation have been proposed, some incorporating ideas from quantum field theory and string theory, aiming to provide a more complete picture of these dynamics. Now, how does inflation explain the uniformity of the cosmic microwave background? Inflation theory offers a compelling explanation for the uniformity observed in the cosmic microwave background, CMB, the faint afterglow of radiation permeating the universe from the Big Bang. The CMB presents a nearly uniform temperature across the sky, with incredibly slight variations, about 1 part in 100,000. This uniformity, coupled with the isotropy, sameness in all directions of the universe on large scales, posed a significant puzzle for cosmologists before the advent of inflation theory. Given the vastness of the universe and the finite speed of light, regions on opposite sides of the observable universe haven't had enough time since the Big Bang to exchange heat or light and come to a thermal equilibrium. This dilemma, known as the horizon problem, raised questions about how the CMB could be so remarkably uniform. Inflation addresses this conundrum by proposing a period of exponential expansion shortly after the Big Bang. According to inflationary theory, the observable universe expanded from a tiny subatomic size to a macroscopic size in less than a trillionth of a second. This rapid expansion means that regions now on opposite sides of the observable universe were once close together, well within causal contact, before inflation drove them apart. These regions were able to come to a thermal equilibrium, sharing energy and smoothing out any temperature differences before being stretched across the sky by inflation. Thus, when we look at the CMB, we are seeing a snapshot of a much smaller, uniform universe stretched across the vastness of space, explaining its uniform temperature. The slight variations in temperature that we do observe in the CMB, then, are attributed to quantum fluctuations in the density of the universe that were present just before inflation occurred. These fluctuations, once minuscule, were amplified by the inflationary expansion to stretch across cosmic scales, forming the seeds for the large-scale structure of the universe, such as galaxies and clusters of galaxies. The patterns of these fluctuations in the CMB have been precisely measured by experiments such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, providing strong support for the inflation model. Antimatter is a fundamental concept in physics, mirroring the properties of matter, but with opposite charges. For every type of particle that constitutes matter, there exists a corresponding antiparticle that makes up antimatter. These antiparticles possess the same mass as their matter counterparts, but have opposite electric charge and other quantum numbers. The most familiar examples include the positron, the antiparticle of the electron, which carries a positive charge, and the antiproton, which has the same mass as a proton but a negative charge. The existence of antimatter was first predicted by the British physicist Paul Dirac in 1928, based on his work extending the equations of quantum mechanics to incorporate the theory of special relativity. Dirac's equations suggested the presence of particles that had the same mass as electrons but opposite charge, a prediction that was confirmed in 1932 with the discovery of the positron by Carl Anderson. This discovery was groundbreaking, as it provided the first evidence of antimatter and validated Dirac's theoretical framework. When a particle of matter encounters its corresponding antiparticle, the two annihilate each other in a burst of energy, typically producing gamma rays. This process of annihilation demonstrates the equivalence of mass and energy, as described by Einstein's m²/mc² equation, and is a fundamental aspect of antimatter's interaction with matter. Antimatter is not just a theoretical curiosity, it has practical applications and implications. In medicine, for example, positron emission tomography, PT scans, rely on the detection of gamma rays from positron annihilation to create detailed images of the body. Furthermore, understanding antimatter is crucial for advancing our knowledge of the universe. Cosmologists study antimatter to address fundamental questions about the Big Bang and why the observable universe appears to be composed almost entirely of matter, despite theories predicting equal amounts of matter and antimatter were produced in the universe's early moments. The investigation of antimatter also pushes the boundaries of particle physics, challenging scientists to create, trap, and study antiparticles in laboratory conditions. Experiments with antihydrogen atoms, for instance, aim to compare the properties of hydrogen and antihydrogen to test the fundamental symmetries of nature. These studies could reveal new physics beyond the standard model, offering insights into the forces and particles that shape our universe. Now let's talk a bit about CP violation and how it relates to matter-antimatter asymmetry. CP violation refers to a fundamental phenomenon in particle physics where the combined operation of charge conjugation, C, and parity inversion, P, is not conserved. In simpler terms, it means that certain processes involving the transformation of particles into their corresponding antiparticles do not occur in the same way when the charges and spatial orientations are reversed. CP violation is significant in the context of understanding the matter-antimatter asymmetry in the universe. In the early universe, matter and antimatter were produced in nearly equal amounts during particle-antiparticle creation processes. However, if all physical processes respected CP symmetry perfectly, matter and antimatter would have annihilated each other completely, leaving behind a universe devoid of matter. The observed matter-antimatter asymmetry suggests that there must be processes where CP symmetry is violated, favoring the production of matter over antimatter. This violation of CP symmetry allows for subtle differences in the behavior of particles and antiparticles, leading to a slight excess of matter that ultimately gave rise to the structures we see in the universe today. CP violation has been experimentally observed in certain rare decays of elementary particles, such as neutral kaons and B mesons. These experiments have provided crucial insights into the mechanisms responsible for generating the matter-antimatter asymmetry in the early universe. However, the exact origin of CP violation and its connection to the observed matter-antimatter asymmetry remain active areas of research in particle physics. Can we truly understand the origin of the universe? This question has captivated scientists, philosophers, and theologians alike for centuries. As we delve into the depths of cosmology and particle physics, we uncover glimpses of the cosmic drama that unfolded billions of years ago. Yet, despite our best efforts, there remains a veil of mystery shrouding the ultimate genesis of the cosmos. Theories such as the Big Bang provide a framework for understanding the evolution of the universe from its earliest moments. But when we peer back to the very instant of creation, we encounter a realm where the laws of physics break down and our conventional understanding falters. It is a realm of extreme temperatures, densities, and energies, where the fabric of space-time itself undergoes profound transformations. In our quest to comprehend the origin of the universe, we confront the limits of human cognition and the boundaries of scientific inquiry. Can we ever hope to unravel the mysteries of existence with our finite minds and empirical methods? Or are there realms of knowledge that lie beyond the reach of human understanding? Some argue that the pursuit of understanding is an inherent aspect of the human condition, driving us to explore, question, and seek answers to the deepest mysteries of existence. Others contend that there are limits to what we can know, and that some aspects of reality may forever elude our grasp. How does the concept of nothing fit into modern physics? It's a question that challenges our fundamental understanding of reality. In the realm of modern physics, nothing isn't simply an absence of matter or energy. Instead, it's a complex and dynamic landscape governed by the laws of quantum mechanics. In quantum physics, the vacuum of space is far from empty. It's teeming with virtual particles spontaneously popping in and out of existence, borrowing energy from the vacuum for fleeting moments before annihilating each other. This phenomenon, known as vacuum fluctuations, suggests that even in the absence of particles, the fabric of space-time is seething with activity. Moreover, the concept of nothing is intertwined with the mysteries of the universe's origin. The Big Bang theory posits that the universe emerged from a singularity, a point of infinite density and temperature. But what preceded the Big Bang? Was there truly nothing before the universe began its expansion? or are there realms of existence beyond our current understanding? Research in particle physics has far-reaching implications that extend beyond the confines of the laboratory, offering numerous benefits to society. While the subject matter might seem esoteric, the advancements made in particle physics have yielded tangible outcomes that impact our daily lives. One significant contribution of particle physics research is its role in medical imaging and treatment. Technologies such as PT, positron emission tomography, and MRI, magnetic resonance imaging, have their roots in particle physics research. These imaging techniques are crucial for diagnosing medical conditions and guiding treatment plans, improving healthcare outcomes for millions of people worldwide. Additionally, particle physics has paved the way for advancements in radiation therapy for cancer treatment. Techniques such as proton therapy, which utilizes beams of protons to precisely target tumors while minimizing damage to surrounding healthy tissues, have emerged from particle physics research. These therapies offer more effective and less invasive treatment options for cancer patients. Research in particle physics has contributed to the development of innovative materials and technologies. For example, the World Wide Web, invented at CERN to facilitate communication among researchers, has transformed the way information is accessed and shared globally. Furthermore, advancements in particle detector technologies have led to the creation of more sensitive detectors used in security screening, environmental monitoring, and even archaeological exploration. The pursuit of fundamental knowledge in particle physics often drives advancements in other scientific disciplines. Collaborations between physicists, engineers, and mathematicians foster interdisciplinary research that fuels innovation across various fields. Future discoveries in particle physics hold the promise of revolutionizing various aspects of our daily lives. While some of these advancements may seem distant or abstract, their potential impact on society could be profound. One area where future discoveries could have a significant impact is in energy production and storage. Breakthroughs in particle physics could lead to the development of more efficient and sustainable energy sources, helping to address pressing concerns such as climate change and energy security. For example, advancements in fusion energy research, inspired by the study of plasma physics in particle accelerators, could one day provide a clean and virtually limitless source of power. Discoveries in particle physics may lead to advancements in technology and computing. The development of quantum computing, which draws heavily from the principles of quantum mechanics explored in particle physics, could revolutionize fields such as cryptography, drug discovery, and artificial intelligence. Quantum computers have the potential to solve complex problems exponentially faster than classical computers, opening up new possibilities for scientific research and innovation. Particle physics research, while offering immense potential for scientific advancement, also raises several ethical considerations that warrant careful examination. One such consideration is the allocation of resources. Particle physics experiments often require substantial financial investments and access to sophisticated technology. Critics argue that these resources could be better allocated to address pressing societal issues such as poverty, healthcare, and education. However, proponents argue that investing in fundamental research can lead to unforeseen technological breakthroughs and long-term societal benefits. Another ethical concern is the safety of particle physics experiments, particularly those involving high-energy particle accelerators. While the likelihood of catastrophic events occurring as a result of these experiments is extremely low, some worry about the potential risks, such as the creation of micro-black holes or the release of dangerous radiation. Researchers and regulatory bodies must carefully assess and mitigate these risks to ensure the safety of both experimenters and the public. There are ethical considerations surrounding the dissemination of knowledge and the potential misuse of scientific discoveries. Particle physics research often yields valuable insights into the fundamental workings of the universe, which can have wide-ranging implications for technology, medicine, and other fields. However, there is a risk that this knowledge could be weaponized or exploited for harmful purposes. Scientists and policymakers must consider how to balance the benefits of scientific progress with the need to prevent misuse and ensure responsible stewardship of knowledge. Additionally, there are ethical questions related to the international collaboration and distribution of research findings in particle physics. Collaborative efforts among scientists from different countries are essential for advancing knowledge in this field. However, issues such as intellectual property rights, data sharing, and equitable access to research opportunities can arise, particularly in cases where resources are limited or disparities exist between nations. Ensuring fair and transparent collaboration is essential for upholding the principles of scientific integrity and promoting global progress. While particle physics research holds tremendous promise for scientific discovery and technological innovation, it also presents complex ethical challenges that must be addressed thoughtfully and responsibly. By considering these ethical considerations and engaging in open dialogue, scientists, policymakers, and society as a whole can work together to navigate the ethical complexities of particle physics research and maximize its potential benefits for humanity. As we end our journey in contemplating the emergence of particles from what appears to be nothingness, we are confronted with profound philosophical questions that transcend the boundaries of empirical science. Perhaps, in the cosmic symphony of creation, there lies a deeper truth beyond the grasp of our current understanding, a truth that speaks to the interconnectedness of all existence and the infinite potential inherent in the fabric of reality. Could it be that particles arise not from a void of nothingness, but from the boundless reservoir of possibility that permeates the cosmos? Ultimately, the question of how particles form from nothing invites us to contemplate our place in the vast expanse of the universe and to embrace the wonder and mystery that surrounds us. It challenges us to expand our minds beyond the confines of conventional thinking and to embrace the boundless possibilities that lie at the heart of existence. How do you think particles came to life? How did it all start? Share your thoughts in the comments below. Thanks for watching.